Welcome back, student, to the last lecture of this module and also the last lecture of this course of hydraulic engineering. It has been pleasure interacting with you. So, to go ahead and get started with this topic of pressure distribution under progressive waves. So, you remember we talked about linearized Bernoulli's equation. This equation is given by minus del phi del t plus p by rho plus gz, half rho square plus half u square plus w square. We that term we avoided because of linearization. Now, if we multiply this throughout by rho, the above equation, then the pressure can be given as, you see, if we take p on the other side, it can be written as rho del phi del t minus. So, okay, let me take this. So, we multiplied by rho, so it becomes minus rho del phi del t plus p, because rho gets cancelled here, plus rho g z, and this can be written as gamma. So, p can be written as, if this goes on the other side, this becomes rho del phi del t, and this one becomes minus gamma z. All right. And this is the same equation here. So, it becomes P is equal to rho del phi del t minus gamma z, or plus of minus gamma z. This is the dynamic pressure, and this is the static component, depending upon only the water depth. Now, if we substitute for phi, phi was the velocity potential in this equation, what do we get? P will be, so del phi del t, it will be written as gamma h by 2 cos h k into d plus z divided by cos h k d into sin k x minus sigma t minus gamma z. Okay, so this is the pressure equation. All right. We already know that eta can be written as h by 2 sin k x minus sigma t, and let us assume that cos h k into d plus z divided by cos h k d, if we write as k p, okay, substitute, then the p, this one can be written as, see, gamma h by 2, this will be k p, correct, or h by 2 sin k x minus sigma t is eta. So, we can write, and k p, we say that k p is the pressure response factor. Then we can simply write p as gamma eta into k p minus gamma z. All right. Or p by gamma can be written as eta k p minus z. Now, it is to be mentioned that P was set to 0 to define the free surface boundary condition in Bernoulli's equation, if you remember. However, phi was determined by setting P is equal to 0 at z is equal to 0 instead of z is equal to eta. Hence, this means this particular equation is valid only for negative z. If you want to, suppose this is the free, this is the freezer. So, this is z is equal to 0. So, the above equation is valid only in this region below. We cannot apply this here in this domain, the pressure, no, because it was, because we had derived phi with certain approximations, assumptions. All right. So, P by gamma is eta k p, and I think this is one such equation which should be remembered. K p is cos h k d plus z divided by cos h k d, and eta we already know, it is a sin k x minus sigma t or h by 2 sin k x minus sigma t. Now, if we apply this equation 2.57, so pressure at z is equal to 0 is going to be P by gamma is equal to eta, and pressure at z is equal to minus d, that is at, so this is free surface, and this is at bottom, right, z is equal to minus d is bottom. So, this means if you see n by cos h k d plus d, we know that it is definitely less than d plus eta, alright, because cos h k d is always greater than 1. Since cos, correct. So, under the trough at seabed, the conditions are z is equal to, at trough, wave trough, conditions are z is equal to minus d and eta is equal to minus eta. So, if we substitute that, Kp is going to be cos d minus d divided by cos h k d, or 1 by cos h k d, alright. And n in eta is equal to minus eta, therefore, we will get P by gamma is equal to minus eta by cos h k d plus d, which means that P by gamma is d minus eta by cos h a d will always be greater than d minus eta, because this is greater than 1. It is often needed to determine the surface wave height based on subsurface measurement of the pressure. So, for this purpose, equation 2.7 can be represented as, so if we have subsurface measurement techniques available, so we can actually calculate the n, where n is the correction factor depending upon the period, depth, wave amplitude, etc. This is for the people who are interested more in practicals. So, n has been found that should be greater than 1 for long period waves and n should be less than 1 for short period waves, and n is equal to 1 for linear waves, as we have seen already. So, the pressure distribution under progressive wave is given by this, alright. This is crest, wave crest. So, pressure distribution under wave crest and pressure distribution under wave trough, alright. Good. So, this is the pressure distribution under a progressive wave, alright. So, these terms is important, d plus eta, d minus eta by cos h k d, d minus eta and d plus. So, in questions you can be given, for example, this curve and asked to label what is this quantity and other things, alright. Now, there is something called group celerity, a very important concept. So, when a group of waves or a wave train travels, its speed is generally not identical with the speed of the individual waves. So, if there is a group that is traveling, its speed is not going to be the same as it was traveling alone. Our analogy is, if you run alone and if you run along with the group of people taking everyone together, the speeds will be different, right. So, if any two wave trains of the same amplitude but slightly different wavelengths or periods progress in the same direction, the resultant surface disturbance can be represented as the sum of individual disturbances, okay, based on the principle of superposition. So, for waves propagating in deep or transitional water, the group velocity is determined as follows. So, as I said, there will be superposition of eta 1 and eta 2. So, we can simply write combined eta t as eta 1 plus eta 2 is equal to a sin k 1 x minus sigma t plus a sin k 2 x minus sigma t, because we have assumed that the same, almost same amplitude but different phases, alright. So, using the trigonometry, we write it is 2a cos of k 1 minus k 2 by 2 x minus sigma 1 minus sigma 2 by 2 t sine of this term. This is what we get using the trigonometry, alright. So, the left hand side is k 1 minus k 2 by 2 x minus sigma 1 minus sigma 2 by 2 into t, alright. So, this is a form of a series of sine waves, the amplitude of which varies slowly from 0 to 2a according to the cosine factor. So, we say this is the amplitude of the wave and this is the phase, and the amplitude varies from 0 to 2a depending upon the what the phase is here. So, the point of 0 amplitude or nodes, okay, because it will vary slowly from 0 to 2a, there will be 2a as well, there will be 0 as well. So, the point of 0 amplitude are called nodes. They can be located by finding the zeros of the cosine factor, correct, because if this is 0, right, that is eta max is equal to 0 occurs when k1 minus k2, when the term within the cos is pi by 2 or a multiple of pi by 2. In other words, the nodes will occur on x axis at a distance as follows. If you see, you try to do that, if you rearrange, we can get x node here is equal to x is here, just rearrange, it will be 2m plus 1 pi by 2, 2 will get cancelled from each side, it will be k1 minus k2 plus sigma 1 minus sigma 2 by k1 minus k2 into t. All right. Since the position of all nodes in the function is a function of time and they are not stationary, at t is equal to 0, there will be nodes at. So, at we equate this at time t is equal to 0. So, we will see there will be nodes at pi divided by k1 minus k2 divided, and then there will be node at 3 pi divided by k1 minus k2. Okay, if we start putting m is equal to 0, 1, 2, 3, and the distance between the node is given by 2 pi by divided by k1 minus k2 or L1 L2 divided by L2 minus L1. So, you can be asked to find out the distance between the nodes, and this is an important result that you can remember. The speed of propagation of the nodes and hence the speed of propagation of wave group is called the group's velocity. So, what we have obtained is we have obtained the distance between the nodes. So, now if we find out the speed of these nodes, we can find out the speed of the propagation of the wave group, and this particular velocity is called as group velocity. So, if we find dx node by dt is the wave group velocity Cg, all right. So, if you go to see x node, what was x node? X node was here, and if you differentiate dx node by dt, this term on differentiation will be 0 plus sigma 1 minus sigma 2 divided by k1 minus k2, all right, and this is what is told here, sigma 1 minus sigma 2 divided by k1 minus 2 or d sigma by dk, all right, but sigma is what? K into c, you see, sigma can be written as k into c, 2 pi by l into l by t. So, Cg will be d, instead of sigma we write k into c, and if we differentiate this we are going to get, so differentiation by, I mean, if there are differentiation of dab is a d db dt plus b plus plus b dA dt. So, we have used this rule, chain rule, and we have obtained c plus k dc dk. C remains c here and k so what we do, we write k remains same, instead of dc dk we write dc dl into 1 by dk dl. So, we are actually doing some manipulation here. With terms here, okay, and since k is equal to 2 pi by l, Cg will be c plus k, we write 2 pi by l dc by dl into 1 minus, into 1 divided by minus 2 pi by l square, or Cg is equal to c minus l dc dl, since c square is equal to g by k tan h k d from dispersion relationship. And if we substitute this c here and do dc by dl as well, we will get Cg by C is equal to N, where N is half into 1 plus 2 Kd divided by sin h 2 Kd. So, the derivation you do not have to worry about that much, but this equation is important. Or Cg can be written as group velocity will be C by 2 into 1 plus 2 Kd divided by sin h 2 Kd. This equation is very important to remember. You must remember this equation. So, for deep water 2 Kd divided by sin h 2 Kd is 0. Therefore, Cg group velocity is C naught by 2. C naught is the wave celerity of a single wave. An important result that the group velocity in deep water is wave celerity by 2. So, group velocity is 1/2 of the phase velocity in deep waters. Further, it should be noted that the variables if associated with suffix 0 refers to deep water condition. Wherever we have put 0, that means deep water condition. All right. And deep water celerity you already remember, 1.56 times the time period. There is a table that shows there are some totic variations. So, sin h Kd in shallow waters is Kd, whereas in deep water it is e to the power Kd by 2. Cos h Kd in shallow water is 1 and cos h Kd in deep water is e to the power Kd by 2. Tan h Kd is Kd in shallow water and deep water it is 1. This we have already discussed once before also in a different format, but yes, this is the thing. So, in shallow water sin h 2 Kd becomes 2 Kd. So, therefore, Cg is going to be, you look at this equation, sin h 2 Kd will be 2 Kd. So, this 2 Kd gets cancelled, right. So, it will be 1 plus 1 2, 2 into half. So, Cg will become Cg. Cg will become C, and that is equal to under root Gd. So, in shallow water the group velocity is same as the phase velocities or the celerity of the wave. All right. So, in deep water it is C naught by 2, whereas Cg is equal to C in shallow waters. And in for the normal for the intermediate waters you can use this equation. C is equal to Cg is equal to C by 2 into 1 plus 2 Kd divided by sin h 2 Kd. All right. This is actually for all the waters, but intermediate waters, because deep water and shallow waters we have some approximations, but intermediate waters we can use the same formula. Now, what is wave energy? We have discussed about almost everything. So, we have discussed about the particle trajectories, then we have discussed about this group velocity. Now, we must go towards wave energy. So, total energy is potential energy plus kinetic energy. So, in order to determine the total energy under progressive wave, the potential energy of the wave above z is equal to minus d with a wave from present is determined, from which the potential energy of the water in absence of the wave is subtracted. So, how do we determine total energy in progressive wave? We determine the total energy of the wave and we subtract it with the potential energy of the water in the absence of the wave. So, we get the energy in presence of waves only. So, the potential energy with respect to z minus d of a small column of water d plus eta high, dx long and 1 meter wide can be written as. So, if we have a small column of water d plus eta height, where dx is length and 1 meter wide, potential energy will be gamma A x bar. All right. Area will be d plus eta into d plus eta by 2, all right, into dx. So, the potential energy will be gamma d plus eta whole square by 2 multiplied by dx. So, the potential energy of a small column of water, all right. So, average potential energy per unit surface area is going to be integration of gamma by 2 into, so we have to average over the whole wave period and also average over the entire wavelength, and using the equation below, you see we integrate it, and after integration, if we use n is equal to a sin kx minus sigma t, and then we integrate and simplification, we will get potential energy, total potential energy is going to be gamma d square by 2 plus gamma a square by 4. All right. However, this is the average potential energy per unit surface area of all the water above z is equal to minus d. Now, we should also calculate the potential energy in absence of the wave, when the wave is not there. Okay, when the wave is not there, then there will be no eta in this term. You see there was eta here, right. So, now this won't be there when there is no wave, and we do the same procedure for finding the total potential energy. All right, and this comes to be gamma d square by 2. And the total energy due to the presence of the wave will be the total energy minus the energy when the wave is not there. So, this will become the average potential energy. This one came to be gamma d square by 2 plus gamma a square by 4, and this one came to be gamma d square by 2, and this gives us the potential energy due to waves is gamma a square by 4, where a is the wave amplitude. You have seen how it is derived, but results are more important. So, you must remember the potential energy due to the waves is written as gamma a square by 4. All right. So, this was the assumption we have assumed using this small particle, and by integrating over the entire wavelength and entire wave period, we have obtained the potential energy. So, the method was total potential energy with wave minus the potential energy without waves, gave us due to waves alone. All right. Now, we will also need to find kinetic energy. It is very simple. Kinetic energy is half mv square, where m is the mass of the fluid and v is the resultant velocity. For two-dimensional wave flow, we know it is half under root u square plus w square into dm. dm can be written as rho into dz dx for that definition here, right, dz dx, and under root u square plus w square. So, the average kinetic energy per unit of surface area, if we integrate it over the entire wavelength and wave period, will come out to be, it is a complex it is so many terms, but on applying the simplification of trigonometry, we can get, if we apply these simplifications, you will get these slides. So, you will have more, it will be easy to understand, but more important are the results. So, we can show that kinetic energy is gamma a square by 4. Potential energy was also gamma a square by 4. Therefore, the total energy is going to be, due to the waves alone, is potential energy plus kinetic energy. The total energy is gamma a square by 2. So, the average, this is an important result again. So, the kinetic energy value, the potential energy and the total energy, these equations you must remember, gamma a square by 4, gamma a square by 4, and total energy is gamma a square by 2. So, the average total energy per unit surface area is the sum of average potential and kinetic energy densities, often called as specific energy density. You can also be asked what is specific energy density, for example. So, now we have studied wave energy. It is very obvious that we study wave power. Wave energy flux is the rate at which energy is transmitted in the direction of wave propagation across a vertical plane perpendicular to the direction of wave advance and extending down the entire depth. So, the average energy flux per unit wave crest width transmitted across a plane perpendicular to the wave advance is wave power. Okay. and it is given as E into Cg. This is important. Cg is group velocity and E is the energy that we just derived. So, the power is given as E into Cg, or if you want to write it in terms of celerity, it is E bar n into Cg. You saw that n was this. So, the wave power is nothing, you just need to remember the formula as E bar into Cg, where E bar was gamma A square by 2. Okay. So, for deep water, you know that Cg was half C naught, n is equal to half. So, power is going to be half E into C naught. For shallow water, it will be E into Cg, alright, because Cg is C only. If you assume that the wave propagates from deep water towards the shore and the ocean bottom slope is gradual and there are no undulations and has parallel bottom slope, because you see the wave power is going to be conserved if the wave moves from one depth to the other, okay, because you see this, if there is no loss, it is average energy flux per unit wave crest width, alright, and if we apply the conservation of wave power alright, so you see this is any depth, right. So, E is gamma A square by 2 equal to gamma A is h by 2 whole square by 2. So, this becomes gamma h square by 8, and Cg we know, Cg we know. So, if the wave propagates from deep water to, let us say, any depth, whether intermediate or shallow, so wave power is going to be conserved, correct. So, in deep water it will be gamma h naught square by 8, h naught indicates the wave height in deep water, okay, multiplied by, we have already seen that this is going, Cg is C naught by 2, and this will be equal to gamma h square by 8, this is the wave height at any depth where we want to calculate, multiplied by Cg, alright. This is what this equation is all about, this equation. So, we are conserving power from deep water to any water depth, and if we substitute for Cg as C by 2 into 1 plus 2 kd by sin h 2 kd, we are going to obtain h by h naught is equal to C naught by C into 1 by 1 plus 2 kd divided by sin h 2 kd, or we can obtain h by h naught is equal to under root of, because this is n, sorry, this is n by, this is 2n. Therefore, h by h naught is equal to under root of C naught by C into 1 by 2n, and this is called Ks, where n is equal to half into 1 plus 2 kd divided by sin h 2 kd. So, the above equation is very important again. This represents a phenomena which is called shoaling, and this gives the ratio between wave height at any depth in the shallower waters compared to the deep water wave height, and this relationship is obtained without considering the irregular variation in the sea bottom, and this ratio under root of C naught by C into 1 by 2n is called shoaling coefficient, or Ks. So, until now you saw that we had been able to obtain relationship between deep water velocities and only kinematics, but this is the only equation that we have studied, that if we know the wave height in deep water, we will also be able to calculate wave height at any depth z. So, a very important equation. A very important equation which you must remember. The shoaling coefficient under root C naught by C into 1 by T C 1 by 2n, where C naught is the speed in the deep water, which is 1.56 times t. All right. So, there are some formulas to remember, but remember only the simple ones, the ones that I have already told you. So, by equating the wave power, we have been able to obtain the wave height transformation if the wave propagates from one depth to the other depth. All right. So, the variation of different properties of small amplitude waves are shown in this figure. You do not need to pay too much attention, just we have plotted d by L, c by c naught, ks and n, which you already know. Ks is the Scholling coefficient. All right. So, this is the last topic. The derivation is outside the scope, but what you must understand is that when waves are in motion, the particles upon completion of each nearly an elliptical or circular motion would have advanced a short distance in the direction of propagation of waves. You can check it from those equations as well. Therefore, if they move ahead, that means that the mass associated with them has already moved forward, correct? This mass transport is happening in the direction of the progress of the wave, and the mass transport velocity is given by pi h by L whole square into c by 2 cos h 2k d plus z divided by sin h square kd. So, this is outside the scope, the formula. I do not expect you to remember this particular equation, but more importantly the message is that you must understand that the mass transport happens and then the wave motion is there. Okay. Of course, you must remember that it is a function of h square. For example, mass transport is a function of h square, or is related to how, I mean the way in which it is proportional to one quantity. All right. So, the mass transport speed is appreciable for high steep waves and very small for waves of long period. You can see this equation. All right. So, if it is a long wave, the mass transport is very less, because so if period is long, the length is long. It is a high steep wave, which means it is directly proportional to h square. So, the mass transport will be high for the higher waves. So, this was the last topic of hydraulic engineering, which we have finished now, and with this I would like to close the lecture and also this course. If you have further doubts, please do contact us in the forum, or I will be appearing in some live sessions also. I do not know if we have something kept after this lecture, but if you have, you can send email to my teaching assistants or also post the question in forum. I wish you good luck for your assignment for this particular week and also the final exams. Thank you so much for listening. Have a great year.